In the last lecture, we looked at Poisson's ratio and how we can use it to find the strain in the X, Y, and Z directions. And then from there, we can work out changes in length in the X, Y, and Z directions, and then ultimately our volumetric strain and our change in volume of a particular material. This week we're going to look at a particular application that gives us a combined stress state where we've got at least two stresses in orthogonal planes. We're going to look at thin-walled pressure vessels. For a container to be termed a thin-walled pressure vessel, it needs to have obviously a thin wall relative to its diameter. So a general rule is if the thickness of the material T here divided by the overall inside diameter of the vessel is less than 20, then we can consider it as a thin-walled pressure vessel. And one of the assumptions we make for this is that the stress throughout the thickness is equal. So the stress on the inside of the cylinder is the same as on the outside of the cylinder. If we get ratios of less than 20, then we have to move on to thick-walled pressure vessel theory, where the stresses will be different on the inside and outside. And here we have some examples of some thin-walled pressure vessels. So we can have things like pipes or hoses which contain pressurized fluids, even things like a Coca-Cola can. And here in the middle here we've got a Coke bottle wrapped in gaffer tape, and then it's been pressurized with a hose pipe. And I'm just going to play the video now, and you'll watch and see how it expands due to the increased pressure and then ultimately ruptures.
$160, $170, $180,
So you can see it's expanding now. That in slow motion. So in reality, if this is an engineering situation, then we don't want that to happen. We also may want to calculate the change in volume of that vessel when we're filling it up with a particular pressure. And before we can do that, we need to find out what the stress is in the walls of the material. And that's what we're going to do over the next few slides before we start to look at the volumetric change.
160.
If we have our pressurized cylinder here, little diagram up on the right, and we look along the axis of the cylinder, then we will see obviously a ring like this. And then if we put pressure on the inside, well, it's probably self-evident. If we do that, then the diameter of that pressure vessel is going to increase, and there will be an induced stress in the walls of that vessel. If we look at the side of the cylinder, so we look in this direction, and we increase the pressure, then it will have pressure on the ends of the cylinder as well, so that will induce another stress along the axis of the cylinder, and its length will increase as well. So this radial stress around the diameter we term the hoop stress, and the stress along the axis of the cylinder we call the axial stress. On the next couple of slides, we'll work out how we can work out what those stress levels are, and then hence the strain levels and the change in volume. It will be a combined stress state where we have our circumferential stress, which we call the hoop stress, and we also have the axial stress along the length of the cylinder here. So if you look at here on the diagram, a section of that material, we can see it's got those two stresses on there, and they're both, in this case, because it's a higher internal pressure in this example, so we'd say that this pressure on the inside is pushing out on the walls, then they would be a positive stress, so it will be in tension. What will the hoop stress be? Well, if we look at our pressurized cylinder and we slice it in half along its length, then we'll have a system where we've got an internal pressure, and you can imagine if we had to hold that pressure into that half cylinder that we've got there, we'd have to work against the pressure, and the pressure would be pushing upwards here from that internal pressure, wouldn't it? So if we cut the cylinder in half, we'll end up with pressure inside pushing up from that section surface. So that internal pressure and we'll call that P, and pressure equals force over area. Force over area. Let's just rearrange that equation to make the force the subject. So our force equals our pressure times by the area, and our area then that the pressure is exerting will be the area of this surface here that we've got. So the area will be this rectangle, and that's going to equal D times by L, isn't it? So we can say therefore then our force equals P D L. If we were to contain that, then the material of the cylinder has to work against that pressure, so the material of the cylinder is providing a force along this kind of surface that we've cut through here to act against that internal pressure. So the stress in the wall then is going to equal our hoop stress, that's what we're terming it, and again that's going to be force over area. And in this case our hoop stress is going to be our force, and what is the area of the cylinder wall? Well, it's the thickness T multiplied by L, and there's 1 at each side, so it's 2TL. So our stress becomes 2 times by TL. If we rearrange that to make the force the subject again, so therefore we could say that force equals our hoop stress multiplied by 2TL. And let's just put some numbers on here. So if we look at this equation here, and we'll call that 1, we'll call this one 2, then the forces here both have to balance, don't they? The force that's exerted by the cylinder wall has to match the force that's exerted by the internal pressure. So we could equate 1 and 2 together. So comparing 1 and 2, we have P dL equals sigma H 2TL. So our L's are going to cancel out there, so if we then work out what our hoop stress is, then it's going to be P D over 2T. Let's do the same thing in the axial direction then. Again, if we've cut through our cylinder, our internal pressure, if we had to cap these ends off, we'd be working against a pressure pushing on that section surface there. So that internal pressure P again equals force over area, and in this case we can say P equals force, and the area of that will just be the area of a circle, won't it? The internal diameter, so that will just be pi d to the 4 over 4. Rearrange that again for F, so therefore our F equals P pi d squared. Oh, why did I put to the 4? Should be squared there, shouldn't it? Area of a circle, P pi d squared over 4. And again, we will have the stress within the cylinder walls applying a force equal and opposite to the force inside the cylinder. So we'll have a force pushed here along these this section surface here. So for our axial stress, and in the wall that is, so we'll call that sigma A equals force over area, and in this case our force is over, and the area of this kind of surface here, so it's this area around here, is just going to be pi d. Because it's a thin cylinder, we don't need to distinguish between the internal and external diameters. We just use the internal for all of this. So the length of that circumference will be pi d, and then it's multiplied by the thickness to give us the area. So that will be just pi d, which is the circumference, times by the thickness. So therefore our force in this case is going to equal sigma A pi d t. And again, if we say that that is 1 and we compare 1 and 2, then we will have P pi d squared over 4 equals sigma A pi d t. So our d is going to cancel with the squared term, the pi is going to be eliminated, and if we rearrange that then for our axial stress, we will get P d over 4t. So we've got an expression now for both the hoop stress and the axial stress within our pressurized cylinder. And once we've got that and we know the dimensions of the cylinder and the internal pressure, we can then calculate out the strain, which we'll look at on the next slide, I think, and then we can work out what the change in volume is. Before we go on to look at volumetric strain and change in volume, let's just look at an example to work out what the axial and hoop stress are for a particular cylinder. In this case, we've got an internal diameter of 0.5 meter and a thickness of 10 millimeters, so therefore we can safely assume it's a thin wall vessel, and it's got an internal pressure of 200 kilonewtons per meter squared. So we can simply just work out what those stresses are. So our hoop stress, remember, is P d over 2t, and in this case we've got everything that we need there, so it's 200 times 10 to the 3. Our diameter is 0.5 and our thickness was 0.01. Put the numbers in there and we should get a stress of 5 megapascals. If we do the same for our axial stress, well, I'll do the calculation, but you can probably see straight away that it's going to be half of the hoop stress. We've got 200 times 10 to the 3 times by 0.5, and this time it's over 4 times by the thickness, which is going to equal 2.5 megapascals. Fairly straightforward. Looking at the strain in the cylinder then, we've got a biaxial stress state, haven't we? We've got the hoop stress and the axial stress. And if we put our equations from last week in the terms of our hoop and axial stress, then we'll end up with our strain here for our hoop strain and our axial strain. So we can see here our hoop strain is just like last week, so we've got our hoop stress over the Young's modulus minus Poisson's ratio multiplied by the axial stress over the Young's modulus, and similarly for the axial strain as well. Our volumetric strain for the cylinder actually turns out to be twice the hoop strain plus the axial strain. To get this formula here is quite an involved derivation, and it requires some ignoring of smaller terms. So it's a little bit involved for us here. We're just going to use the formula and accept that it gives us an accurate result for the cylinders that we're looking at. Knowing that strain is change in volume over original volume, we can equate our overall volumetric strain to our change in volume. So we can work out the change in volume of our cylinder here from our values that we've got. So we've got our volumetric strain, and the volume of a cylinder will be the internal area, so it's pi d squared over 4 multiplied by the length. We've got an example here. Then we're going to work out what the ultimately what the change in volume of the cylinder will be given a internal pressure of 1 megapascal. We have a cylinder with an internal diameter of 1 meter, wall thickness of 10 millimeters, so it's a thin-walled vessel, and it's 2 meters long. We've given the E value of 200 gigapascals, so it's probably steel, and a Poisson's ratio of 0.3. So in order to get to our change in volume, we need to calculate all of these things along the way. We'll do that on the next slide. Let's start by working out what the stresses are then. So our hoop stress equals PD over 2T, which in this case we have a pressure of 1 times by 10 to the 6, internal diameter of 1 meter, and a wall thickness of 10 millimeters. And that gives me 50 megapascals for hoop stress. Knowing that, then we know that our axial stress, I'm going to be a bit lazy here, I'm just going to assume that I'm not doing the calculation, that's going to equal 25 megapascals, because we know that the axial stress is over 4T in the equation rather than 2T. And we can use this relationship which we've just mentioned for our volumetric strain. First of all, we need to work out what the hoop and axial strains are, so that's going to be our hoop stress, which is 50 megapascals, over our Young's modulus, which is 200 times 10 to the 9, minus our Poisson's ratio, which in this case was 0.3, multiplied by the axial strain, which is 25 times 10 to the 6, again all over our Young's modulus. And if you do that calculation, I get 212.6 microstrain, so that's times by 10 to the minus 6. We can do the same thing for our axial strain. In this case, it's going to be 25 minus our Poisson's ratio times by our hoop stress in this case, so that's 50. In fact, rather than writing over 200 to the 9 each time, we can just put that under both of those, can't we? And that gives me a value of 50 microstrain. So we have so far we have our hoop stress, our axial stress, our hoop strain and our axial strain. Our volumetric strain, hold on, get the right colour, equals twice our hoop strain plus our axial strain, so that is going to equal 2 times by, and it's 2 on 2, and that's going to be plus our axial strain, which is 50, which equals 475 microstrain. Our change in volume then, delta V, is going to be our volumetric strain times by the volume of the cylinder, which is going to be 475 times by the volume of our cylinder, well, the area is pi, times by the diameter, which is 1 squared over 4, times by the length, which was 2 meters. And if you put the numbers in there, it should come to 746 times 10 to the minus 6 meters cubed. Or in millimeters, it's 746 times 10 to the 3 millimeters cubed. Oops. So fairly straightforward, quite a number of steps in there to get there, but it's just plugging the numbers into those equations that we've got. We can do the same thing for a spherical pressure vessel as well. And if we just go through the calculation like we did for the hoop and the axial stress, that's highlighted here on this slide. I'm not going to go through it in too much detail. It's really just the values of the areas that we're working with change. But what we'll appreciate with a spherical pressure vessel is that we have the same stress in all directions. It doesn't matter, it's the same whatever orientation you look at. So it's always going to be the same stress in these two orthogonal planes. It doesn't matter which way you look at it. And if you go through the calculation, you'll end up with this expression here in the red box. And I've called it the hoop stress, which is what it's normally referred to. But you'll notice the equation there is the same as the equation for the axial stress in a cylindrical pressure vessel. So that kind of means that the hoop stress, or the maximum stress in a spherical pressure vessel, is always half of that that's in a cylindrical pressure vessel. So therefore, that's why you'll see high pressure cylinders containing things like carbon dioxide or whatever else are usually a spherical shape in order to minimize the stresses. In fact, even cylindrical vessels tend to have rounded ends on them to reduce the stress around the ends of the pressure vessel. The same relationships hold for the strain in a spherical pressure vessel as they do for a cylindrical one. So for our strain, in this case, it's going to be the same in all directions. Then our hoop strain is the hoop strain over the Young's modulus minus Poisson's ratio multiplied by the stress in the orthogonal plane, which again is the hoop stress. So it's Poisson's ratio times by the hoop stress over E. We can just combine that into a more elegant format here in the red box. And again, looking at our volumetric strain, then we can prove that the volumetric strain is this here. We have the twice the hoop strain plus the strain in the other direction, which again is the same hoop strain. So our volumetric strain in a sphere is going to be 3 times that strain that we've calculated. If we know that the diameter of the sphere, we can work out its volume, and therefore we can work out what the change in volume would be just like we did in the previous example for a spherical pressure vessel as well. If we are putting say a liquid into one of these vessels and pressurizing it, what happens to the liquid? In the liquid, if we're pressurizing it, it's going to get a compressive force in all directions, and therefore we'll get a pressure pushing on that volume of fluid, and consequently it will get smaller, it will compress slightly. And we can look at that compression, and it's very similar to looking at Young's modulus for a direct stress or strain in a solid material. Then here we can look at our pressure versus, so that's our stress, the pressure stress, against the volumetric strain, and we'll get a straight line for this isotropic material, this isotropic fluid. And the slope of that we term K, and that K is called the bulk modulus for that fluid. Our definition of bulk modulus then is our volumetric stress over volumetric strain. So K equals P over epsilon, and we can rearrange that to give us our volumetric strain here, knowing that volumetric strain is changing volume over original volume, rearranging for our change in volume and substituting our pK in for our volumetric strain. We can work out the change in volume of a fluid due to a pressure P as being the pressure times by the original volume divided by its bulk modulus. The total change in capacity of a system then is the combination of the expansion of the cylinder or sphere and the compression of the fluid within that. And that can be quite important with a lot of systems here. If we look at a braking system as an example, then we use a lever mechanism when we push on the brake pedal to compress fluid in the master cylinder, which then is taken by the brake pipe, that pressure, which then in turn moves the cylinder within the caliper to apply the brakes. And we have some limitations on this. Well, first of all, we've got an amount of energy, haven't we, that we need to dissipate. So this energy here from the vehicle that we want to slow down. And we've got some limitations here on the brake pedal, because we can only have so much movement of that pedal for us to be comfortable in pushing on that pedal with our normal range of movement. We can't have that too large, that amount of movement. So it kind of limits the ratios that we can get in terms of movement of your foot when you apply the brake pedal to the pressure that we can apply on the brake caliper. And if we start to lose some of this volume, so one, if these cylinders start to expand here and expand here, and the fluid starts to compress, it means that we get less pressure for the amount of movement on the pedal. So it's quite important when we design systems that we take this kind of thing into account. And if you think of brake fluid in your brake system in your car, then it's a specific oil because it has a very high bulk modulus, which means that it doesn't compress very much when put under pressure. This slide just shows the three moduli that you'll have come across in this module this year. First of all, you'd have looked at Young's modulus, our E equals stress over strain, and that will be for direct stress. If we've got torsion or shear, then we need to look at the shear modulus, or the modulus of rigidity. We give that the letter G. So our modulus, shear modulus, is torr, which is our shear stress. So this is our shear stress, torr, over gamma, which is our shear strain. And the bulk modulus that we've just introduced here, K, is our pressure, P, over our volumetric strain. So that just shows the three moduli that we often come across in engineering problems. And we can relate those three moduli together, and if you notice, there's all of these different formulas here going from the top to the bottom. We've got things like that. We can relate the shear modulus to the Young's modulus, we can relate the shear modulus to the bulk modulus, and so on. But if you look at all of these expressions here down from top to bottom, there's one thing that is common in all of them. All of them involve Poisson's ratio to give us that change, or the relationship of change in one direction due to a stress in another direction. Let's look at a final example then. It's the same as the one that we've just done. So all of the cylinder and the volumetric change of that will be the same. But in this case, we're considering the bulk modulus of the fluid, which in this case is 2 giganewtons per meter squared. So we've already done the change in volume of the cylinder. Let's look at the change in volume of the fluid then. Then our change in volume, remember on that last but one slide, it is PV over K, and that's going to be our pressure. So the pressure in the example was 1 times 10 to the 6, and the volume is pi times by 1 squared over 4. It's a meter diameter times by 2 meter length, and that's all going to be over our bulk modulus 2 times by 10 to the 9, which equals 785 times 10 to the minus 6. And just think about that for a second. This 785, it's actually going to be a minus value, isn't it? It's going to compress. The fluid is actually going to take up less space, when it's under pressure. So effectively our total change in volume then, so our change in volume is going to be, so I'll just give a little T for total, is going to be our delta volume of the cylinder plus our change in volume of the fluid. So that's going to be, what do we get? We got 746 for the change in volume of the cylinder, and that's going to be plus 785 times by 10 to the minus 6 for the fluid. And again, that's a plus because we can actually get more fluid in. So that will give us a value of 1.53 times 10 to the minus 3 meters cubed. So if we were filling this cylinder up, then from our initial conditions where we've got the pressure, the fluid which isn't under pressure and the empty cylinder, we fill that up. Once it's full, in order to achieve that pressure of, what was the pressure, 1 megapascal, then we would effectively need to pump in 1.53 to the minus times 10 to the minus 3 meters cubed more fluid in order to achieve that pressure. That then concludes the couple of weeks that we're looking at for Poisson's ratio and thin wall pressure vessels. What I'd like you to do now is to go through the tutorials on thin wall pressure vessels. Make sure that you can do all of those and that you're okay with the Poisson's ratio tutorial sheet from last week. Like always, if you've got any questions or finding anything difficult, just contact me and I'll try my best to help you out. Okay, thanks for listening. Bye for now.